And hello, everyone. I'm Zheng Han, and I come from Tsinghua University in China. Today, we will show you how we perform the hat trick once again in browsers. OK, so firstly, let's briefly introduce ourselves. My partner, Nawam, often known by the nickname Sakura, works as a security researcher at the 360 Vulnerability Research Institute. And I'm Zheng Han, currently pursuing a master's degree at Tsinghua University in China. We focus on vulnerability hunting in browsers, primarily in Chrome. As top researchers for both Chrome and Facebook's vulnerability reward program, we have made multiple presentations at Black Hat. Next, this is the organization we represent, the 360 Vulnerability Research Institute. This is our agenda, where we will introduce the courses and exploitation of 4 vulnerabilities. The first 2 are vulnerabilities on the Chrome side, and the last 2 are vulnerabilities on the Firefox side. OK, so the first part is a callback issue, which is hidden in the runtime support code logic and is related to a new JavaScript proposal. This vulnerability was identified by us just before it was about to be included in the release version, and was reported to Chrome, earning us a $16,000 render remote code execution exploit bounty. Before diving deeper into the root causes of vulnerability, let's first have a brief understanding of the background knowledge. In 2015, a new data structure set was introduced into the JavaScript to make the developer more easier to understand, to make it more easier to code. However, as you can see, the functions available in this set structure are very limited and provide only some very basic methods. So all of these methods operate on the set itself. So if we want to perform some operations on 2 sets, such as getting layer intersections or union, what should we do? The answer is pretty simple. You have to write your own functions to handle this situation. You need to traverse the 2 sets, compare the elements, and then take out the elements that meet the conditions, and put them into a new set. And finally, return the set to the caller. The whole process is very tedious. TC39 has made a new proposal in the last 2 years that introduces more useful methods such as the union and the intersection. And you do not need to write your own functions anymore. It's very convenient for you to compare and operate on both sets. However, Weight Engine introduced a callback vulnerability when trying to support this feature. Let's take a look at the proof of concept, which is listed in the left of the slides. As you can see, the POC is pretty simple. First, we create 2 different set structures, then define a callback function on one of the sets, and then call its disjoint from function to operate both of sets. This function will be triggered when we try to take the value of property size on V1. In this callback function, it only cleans all the elements on V0 sets, and the method is disjoint from will trigger this callback function internally. On the right side of the slide shows the error output of V8 when trying to execute the POC. The error message suggests that there may be a type confusion vulnerability because it tries to use an object as if it were an object of another type, which triggers a debug check. How this vulnerability is triggered? Actually, it's very easy to understand. Let's take a look at the V8 source code. When executing newly implemented methods on sets, we first try to take out the pointer of backend store from the JSSet object and store it into a variable table. Then we execute getSetRecord function, triggering user-defined callback function when fetching the value of property size. However, the V8 developers did not take into account side effects of the getSetRecords function, which can cause the previously fetched pointer to become obsoleted. That's a problem. Very simple but interesting. As the POC demonstrates, triggering vulnerabilities is very easy. Fixing this vulnerability is also easy. Just move the getSetRecord function that may call the callback function forward so that there's no callback issue. So how to exploit? Unlikely the callback issue with array types that has occurred in previous versions of V8. The callback vulnerability in sets cannot be easily exploited through methods like modifying the array length. Therefore, we must gain a deeper understanding of sets implementation in order to exploit this vulnerability. When exploiting V8's vulnerabilities, one of the most common exploits is called fake objects. As the name suggested, if we can fake an actual memory controllable object to make it fake as a JS array, we can use this fake JS array to read and write to arbitrary addresses in the V8 heap, and thus achieve remote code execution. However, the hardest part of the whole exploit process is actually the first step. How do we get such a memory controllable object through the vulnerability? We need to dig a little deeper to understand the related object model. As demonstrated in the slides, there are two object models. The first is JSSet. As you can see, it holds a pointer to an ordered hash set. All the elements of JSSet are actually stored in this hash set. The second is ordered hash set. The blue marked element count property is what we are going to focus on next. Normally, it's a small integer that represents the number of elements currently stored in the hash table. Here is an example where we create a JSSet with integer 1 and integer 2, and the element count on the table is 2. Let's take a look at the JS examples on the right. At first, we create a set structure with 2 elements. The internal memory layout of V8 is consistent with the examples in the object model we introduced earlier. The variable V0 takes a pointer to an ordered hash set storing 2 elements, and the element count property is a small integer of 2. Can you still remember the clean methods involved in the proof of concept? What happened if we call the clean method on the sets? After executing the clean function on variable V0, something will happen. V8 first creates a new empty ordered hash set, then change the pointer on the JSSet to point to this new hash table. One thing we need to keep in mind is that with this new hash table, the element count is still a small integer, 0. However, the element count property of the ordered hash set structure that JSSet previously pointed to is modified to be a pointer to the new hash table. That previously hash table was also considered obsoleted. In this way, we can see that the table held in the V8 code after the vulnerability is triggered will have its size property changed from a small integer to a pointer. In this case, the property next table and the property element count shares the same memory slots. Finally, let's take a brief look at why V8 implements code logic that make ordered hash set table obsolete. As we can quickly understand from the slides, the obsoleted table is designed primarily for iterators. The main way to determine whether a hash set is obsoleted or not is whether the value stored in the element count property is an integer or a pointer. The final question is how to obsolete ordered hash sets. The process can be triggered in 2 ways, either by adding or removing elements so that their length reaches a certain threshold, at which point V8 obsoletes the original ordered hash sets and creates a larger or smaller ordered hash sets, or by directly executing the clean function. In these exploits, we are using the first methods. Get back to vulnerability exploitation. From the previous analysis, we knew that the table variable holds an obsoleted hash table after the vulnerability is triggered, and the size field on the obsoleted hash table is a pointer instead of a small integer, which is called next table. So how do we leak a pointer to control the memory? Let's ignore whether the memory is controllable or not, and let's first try to leak out a pointer to an object that shouldn't have been in the user layer in the first place. While browsing the source code, the method SetPrototype.Union gets our interest. These methods will copy all the memory contents from the obsoleted hash table to a new one, and use this newly created hash table to create a new JSSet and return. Since the union methods makes a complete copy of the entire obsoleted table. Therefore, the table of JSSets returned by these methods is also obsoleted. Repeat again. The property next table and the property size share the same memory slots in ordered hash sets. We can then try to leak this next table value by accessing the size property of the JSSets. We have made very minor changes to the POC. We replace the methods called with union and then get and print the size on the set objects returned by the union function. You can see that it prints out the internal structure ordered hash sets, not a regular integer. But leaking out one such internal ordered hash set doesn't really help our exploits, and we cannot make any changes to the internal structure or read sensitive data. If we can control the leaking next table pointer, offset this pointer slightly this way, the next table pointer in the obsoleted ordered hash sets will be offset to user controllable memory, making it easier for us to subsequently fake the objects. Once again, since the next table and the size property share the same memory slots in obsoleted ordered hash sets, we can manipulate the next table pointer by adding or deleting elements on this JSSet, which holds this obsoleted ordered hash sets. When the next table pointer can be manipulated for a slightly offset, what we only need to do is lay out user controllable memory objects such as the JSArray in front of the obsolete ordered hash sets objects. So let's the leaked pointer point to the mid position on the JSArray, and we can modify the data on the JSArray as expected, and then leak the next table pointer to the user for fake the objects. In this way, since we have successfully faked JSArray objects of controllable length with a controllable backing store pointer, we have the ability to read and write to arbitrary addresses within the V8 heap memory. At that time, the V8 heap sandbox had not yet formed a security boundary, so we could exploit this powerful vulnerability to reach remote code execution through its powerful exploit primitive. In the next part, we are going to introduce the issue of missing checks due to a wrong assumption in code optimization. This vulnerability and the classic callback vulnerability above have relatively simple root causes, but this vulnerability involves code optimization design. Okay, so the most important and the complex part of the V8 engine is the combination optimization part. The first things we need to understand is the design of checkmap node. There is no way to do any advanced optimization of the target function without being able to determine the type of the arguments, because the caller is likely to pass in a variety of different types of arguments when calling the function, the target function. To get around this, we use feedback from the functions previous execution to assume the type of its arguments. And this is what the check map node does. When the optimized function is called, the check map node will determine whether the type of current incoming parameter is the expected one, and then executes the specialization code behind the anomaly. If it's the non-expected one, then it needs to optimize the function to prevent the type confusion. Since the check map is a runtime check, it's necessary to perform this check before assuming that the parameter is a certain type, and then perform refinement operations such as uncheck pointer dereferences. This design introduces some performance overhead because conventionally, a function's arguments will always be of the same type. In this case, it's actually unnecessary to check the type of parameters each time the function being called. This brings us to the key points we are going to introduce, the map dependency. Check map is more likely checking before a piece of code that relies on some type assumptions, kind of like type guard. Stable map dependency is even more like checking for the codes, which is possible to break the type assumptions in of the optimized function. The third points on the slides may not be clear. What's the stable map and what's the type transition? Here, we have prepared examples that demonstrates what a stable map is. Firstly, we create two objects of exactly the same type, variable old map and the new map. The type of both objects shares the same map with only one property x. Initially, these two variables share the same map, and at this point, there are no other objects whose type is transitioned from this map. Therefore, the current map is marked as stable with the box highlighted in the blue. Okay, let's do something interesting. We assign a value to the property A of new map, making this object to create a new property A. After completing the assignment operations to new map, you can see that the map of variable new map is marked as stable, and the map of the variable old map is no longer stable, as there is objects transitioning from this map to another. The most intuitive understanding is that until now, if there is no path to transition from one map to another, this map will be considered stable. Let's take a look at how it works in code optimization. In this example, the function to be optimized, which is called func, will retrieve the property saved in parameters and return it. Before optimizing the function, we create a suitable object and pass it into func to optimize the function based on the execution feedback. Then we use the same procedure to create another object named obj1. The purpose of using the same steps to create another object is to prevent map transition. However, we do not use the list obj1 next, but once again use the previous object variable to call the func function. This process will not trigger any code de-optimization, and it is also easy to understand because the parameter type passed in when calling the function are always the same. What would happen if such a line of code is added to the previously code? This obj1 variable has no use and should not have any impact on the optimized function. The operation on this obj1 variable should not cause any code de-optimization. However, code de-optimization did occur, as described in the figure. The reason is that code dependency is broken due to map transition. Very interesting, right? So for stable map dependency, there are two ways to hunt the vulnerability inside this component. The first way is to find the logic where the compiler depends on a map but forgets to register it. Another way is to try to find a code path to break the type assumption without triggering the callback function that de-optimizes the code. The commonality between these two ways is that they break the type assumption on the optimized function, leading to type confusion vulnerability. Let's take a look at this vulnerability. In machine optimization reducer of Turboshaft, it attempts to optimize the mapped rows and directly operates on the objects. To keep the object map assumption, we first try to we will attempt to create a stable map dependency before optimizing map rows. However, there are slightly discrepancies in determining whether a map is stable. It's considered stable only when a map is not further specialized to other maps. This approach is a bit interesting for primitive types such as string, because primitive types cannot be changed, and the maps of these types are always considered stable. However, primitive objects do not necessarily mean that their map will not change, which allows us to try changing layer types through primitive objects without triggering an optimization callback. In this way, we will ultimately cause the type confusion. We can take a brief look at how some developers fix this vulnerability. The developer adds a whitelist at the if statement with only optimize the types in the whitelist, such as JS objects, while directly optimizing other simple primitive types that can be optimized. As for other types that are not included here, such as string, they will not be optimized. Now we have reached this exciting moment. In these previous sections on the root cause of vulnerability, we have already introduced the way to triggering this vulnerability. Due to the inability of stable map dependency to detect map changes of primitive type such as string, we can change the type of incoming parameters without triggering an optimization. Without triggering the optimization callback, resulting in type confusion. The entire vulnerability exploitation process is divided into 3 steps. Let's verify the vulnerability exploitation strategy. Firstly, we create a string variable of type thinString. Afterwards, we created a function called checkcs to be optimized, which has a simple function of reading a value from a specific offset position in this variable string and returning it. Then we optimize the checkcs function manually. At this point, the checkcs function will establish a stable map dependency for thinString. Before calling garbage collection, when we call the checkcs function, we can see that the entire function can process still, the entire function call process still returns the correct value. However, after completing garbage collection, we immediately trigger a crash in next function call. Let's take a look at this string object model. We can clearly see that the thinString object does not actually store string data, but rather holds a pointer to sequence string. This string content is actually stored in the memory of the sequence string structure. In other words, thinString is a reference to the sequence string. So what happens if the optimized function mistakenly identifies the sequence string as thinString? The answer is obvious. We will be able to freely control the pointer values on the thinString structure. Before triggering garbage collection, the variable string references the thinString object, which is in turn references the sequence string that actually stores character data. However, after triggering garbage collection, we discovered that sequence string was already in the old generation memory, so there was no need to move the thinString object from the new generation memory to the older generation memory and update the pointer on it. Instead, the pointing relationship of a variable string can be directly updated, pointing directly to sequence string and releasing useless thinString. Since the function checkcs still assumes that the variable string is of type thinString, The operation of reading data from the string in the function will be specialized to obtain the pointer on string, dereference it, and reading the data from pointed memory. In this way, we can trigger vulnerability by adjusting the string content to read arbitrary addresses within the weight heap, thereby causing sensitive information leakage. This shows how we trigger vulnerabilities to leak the base address of the weight heap. After we trigger garbage collections, calling the checkcs function will successfully leak the base heap addresses. We create a special string which represents a 4 bytes data with a value of 1 at the memory level. In this way, we can use this type confusion vulnerability to arbitrarily read data from the first page on the weight heap. We can find the base address of the weight heap on that page, which is considered as sensitive information. Because string belongs to primitive type, we cannot make any memory modification through type confusion. However, from the vulnerability patch, it can be seen that besides the string type, there are quite a few types that can be attempted to trigger through this vulnerability. Due to the time limits, we haven't done any further research here, and you can give it a try if interested. In the next section, I will introduce a regrettable Firefox remote code execution 0-day. This vulnerability also existed in the implementation of a new feature, the WebAssembly Garbage Collection, which started to be supported in all major functions last year. But 2 months after I kept it, the vulnerability was internally discovered and fixed by the Firefox team. Let's learn something about WebAssembly. First, you need to write a C code, compile it, and generate the assembly code. And finally, generate WebAssembly bytecode. Afterwards, this code will be placed in the JavaScript code for execution. The WebAssembly Garbage Collection proposal introduces several new types aimed at enabling more complex data structure directly in WebAssembly, such as structure type and array type. With garbage collection supports, the process of initializing WebAssembly instances involves sequentially initializing imported function, memory, tables, text, and types. Please note the initialization order here, where the structure and array type definitions are initialized last. Interestingly, the new WebAssembly standards introduces a feature that allows adding an optional initializer expression to table definitions for element types lacking an implicate default value. Firefox implemented this standard last year. So here is the key code for array initialization. Please note that when creating array variables with the initializer expression, the array type has not been initialized yet. The initialization of the type was mistakenly placed at the end. As a result, all members variables of type-defined data are at their default value of 0 at this time. This leads to element type size being 0 as well, and the calculated total array size, outline bytes, also turns out to be 0. When outline bytes is 0, a small memory space is allocated for storing the array. Since non-elements can be any controllable value, this enables us to perform out-of-bounds reads and writes operations of any length. This is the patch of the vulnerabilities, requiring only simple adjustments of the initialization order. Then it killed my 0-day, as you said. Once we have constructed an array with controllable length but minimum memory allocation, exploiting this vulnerability becomes trivial. We will skip this slide to the audience because the time limits and it's a little complicated. However, the details are released in our white paper. In the following section, we will discuss the issue of integer overflow. Compared to the initialization order arrow mentioned earlier, the root cause of this vulnerability is relatively simple. With the introduction of WebAssembly Garbage Collection objects, Firefox has also implemented the related just-in-time optimization code for them. However, integer overflow issue in this optimization code leads to controllable array out-of-bounds reads and writes. In the SpiderMonkey engine used in the Firefox browser, when creating an array, its size needs to be specific. This size is checked at runtime to ensure that the allocated memory size does not overflow. However, the overflow check performed by the multiplication use sign checks, which allows certain special values to bypass this check. As you can see, the proof of concept is straightforward. The first, we create an array with an initial value of hex 11223344, size of 5. Then we create another array with the initial value of linx.beef and a size of hex FFFF, a special value that can bypass sign checked overflow. The image below shows the error outputs when SpiderMonkey attempts to execute the proof of concept. The error message indicates that the program has crashed. So how to exploit? When exploiting SpiderMonkey vulnerabilities, we typically aim to construct primitives of arbitrary read and write operations, but we need to know the object model first. This is a WebAssembly array object model. The member we need to pay attention to are highlighted in blue, namely num elements and data. Num elements represents the number of elements which can be specified by our parameters. The data pointer points to the beginning of where the array's data is stored, typically located just after the WebAssembly array object. If we use array new to create two arrays, so what would the memory layout look like? The starting position of the second array object will be after the memory region where the first array stores its data. In other words, if the first array is an out-of-bounds read-write array, we can read all the data after the first array's data area out-of-bounds. And at the same time, we have also modified all data after the first array's data area out-of-bounds. Returning to our initial questions, so how do we convert this out-of-bounds read and writes into arbitrary read and writes? First, we can utilize out-of-bounds read to read the stack data after the first array's data area. For example, we can read the array contents pointed to by the data pointer on the second array. Or we can read the data pointer itself in the second array. In this way, we can obtain a stack. Related address. Through this powerful exploitation primitive, we can leverage this vulnerability to achieve remote code execution. In the last lesson, we will demonstrate two remote code execution demo, and these two are relatively simple. The first one is a callback issue in runtime supports, and this is a video. First, we will try to compile the V8 engine and run the proof of concept multiple times, and then we will get the shell. The second is an vulnerability on the Firefox. We just simply run the proof of concept, and a calculation will finally pop up. That's all. Thank you for your listening.